Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Manic Miner, published in 1983 by Software Projects, developed by Matthew Smith and Chris Lancaster. I remember this game when I was about 10 or 11 years old at the time. I had the tape version, and it was actually really quite easy for me to copy it for my friends as well, so they also benefited from me having the tape version. This game was really popular with me at the time on the Commodore 64. I didn't have that many games back in, 1983 or 1984. So I used to play this one to death. I don't think I was actually ever able to complete it, especially not without cheat codes. It is really tough. If you leave the introduction sequence on this screen, then actually it will loop through some of the levels, so we'll let it do that. Now, I've noticed actually that when the looping levels are displaying, I'm actually not playing at this point. There you go. The first screen spends a very long time. I think the countdown timer is a bit bugged in this version of the game. But anyway, the first screen took ages to flip over. And then the next screens, which you can see as it goes through the attract mode, are actually displaying quite quickly. But the thing is that you can, very briefly, control the player character. And there's no collision detection with the player character and the enemies. You can't die to the enemies, which is really quite odd. But the game seems to be set up so that each screen only shows for a short amount of time now, and then does that screen flash effect and then kills you. But now you can hear the music the second time around is a little bit bugged as well. So here we are. I'm trying to play it properly now, and not doing too well on this game. As I say, it's quite tough. You need to actually learn, and in this case relearn, where you need to jump properly and how you need to jump properly. And that's how you don't jump properly, because my head hit the bush or spiky thing or whatever it is. So the eagle-eyed of you might notice that the screen is a little bit smaller than the standard Commodore 64 screen. I think that's probably because it's more like a direct conversion from the original Spectrum version, I think. Here we go, jump. Yay, managed to get it. Can I jump and get... No, because I'm an idiot and I jump too quickly. I don't know why I jump up there. There's enough space for me to walk underneath rather than jumping up and trying to time it with the enemy. Okay, the music's back to how it should be now. Now you see I'm automatically jumping up. Yeah, okay, no, see, I'm not very good at this game. Quite rubbish, in fact. So here we go. Let's complete this screen. This game was actually an inspiration for me to try and do similar kind of games. But being quite young at the time and not technically very capable, I found it really hard. I wanted to try and draw graphics like the main character here. I think his name is Miner Willie, isn't it? I would spend ages drawing out the pixels on graph paper and then calculating the sprite definition values that I would then type into data statements and then view in a basic program. Wow, there we go. I managed to do the first screen. And of course this screen is even more difficult, because I'm not very good at this game. Yeah, no, I'm trapped now, right? I can't jump anywhere, and the stupid penguin. So the graphical variation in this game is actually pretty impressive for the time. Yeah, okay, for the time, I was going to say, and then I got killed. So anyway, let's have a look at the technical details. Let's have a look at the tape file. Now we can see actually that reading kernel bytes, there's a whole bunch of kernel bytes. There is a very large amount of data. There is a first very small file, relatively speaking. And if I put a breakpoint there, then we'll be able to see where the first, it doesn't actually auto start. It's a standard basic starting basic program with a sys statement at the very beginning. So we'll put some breakpoint right at the beginning. We've got all of these nice labels which will help us to see what's going on. So let's load that tap file. Here we go. We can see in the character screen, debug view up in the top right, we can see that there's a small amount of loaded data. We can see that the breakpoint has hit on the expected place in memory. It's just starting just after the basic sys statement. We can see that the tape buffer actually is practically empty, apart from the usual low and high start byte and end byte addresses, and also the text for the file name. We can have a look at the disassembly for all of this. So we can see it's sending 8 to the chart out routine. It's then looks like it's claiming the stop vector. Yep, it's claiming the stop vector. It's also claiming what looks like the user vector at 289. It's jumping over itself a little bit, actually. So the user vector is being set, definitely the stop vector. It looks like it's pointing the stop vector to actually execute the code at 84A, which just increments the border and then jumps through the user vector at 32E, indirected jump. Now, it being the standard kernel load, which you can see happening at 844, which is the JSR load, just after the set name, and the set LFS, the file. Yeah, so the stop vector will get called by the standard kernel load routine, and then it will just execute the increment with border and then jumping through the user vector. So there is no real turbo loader here or anything like that. It's just using the normal kernel loader and just incrementing the border to give some visual cues about what's going on. There we go, just double checking, we got the user defined vector there. I don't know why they bothered to set up the user defined vector when they could just jump to the address straight away, but okay, never mind. It's not like it's hard to figure out this code. It's not really obfuscated in any way, shape or form, really. There's no descrambling going on. There's no complicated timer routines being triggered or anything like that. There we go, 328 points to 084A, which is as expected. F6E1 is what is in 32E and 32F. Looking at this as well. 32E being the user vector that we were just looking at just now. It's setting the number of characters in the keyboard buffer as well, with a store to 289. Maximum number of bytes in the keyboard buffer. We can see the final jump there at 847, which is 24000 in hex, which is labelled there as the start of Vic2 Bank 1, which it is, but it is also the start of the code. If we let these standard kernel load routines continue, we can see it's getting into the stop vector there by jumping indirected through the stop vector as we would normally expect. And then we can see it jumps back to F6E1, which is what we expect. There we are. It's just exiting the interrupt there. So whoever wrote this just basically identified what they needed to jump to exit the interrupt. And I don't know why they jump indirect through the user vector, but okay, that's fine. So this, what looks like a turbo loader, isn't. We know that it's just doing an increment of the border color. Yes, border. With the screen off, the border color covers the whole screen, of course. This is where it's just started storing information into the cassette buffer again. We just put a breakpoint there just to really verify that that's what it's doing, and yes it is. I mean, there was so little code loaded it wasn't able to do anything else, was it? We can see that it's filled the cassette buffer now with standard code. There's nothing hidden in there. The low and high address, there we go, D000 and B000. So we know that code is going to start loading, or code or data or whatever is going to start loading at D00, which is the last screen here in the bottom right hand corner, down a page, down 256 bytes in decimal. There we go, we can see it started loading, quite slowly because it's the kernel load. Now this is quite an old version of ICU. I think there might also be tape traps or kernel traps enabled. Anyway, you can see here that it's straight away it's starting to load some character set data. This doesn't look like it's compressed or anything like that. We can see what it looks like, the title screen data coming in there, the Manic Miner logo, press return to start. See, it's well, the message is straight in there. This looks like might be a bitmap. There's another character set further down. Now you might notice that this character set data looks a bit short. There doesn't seem to be too many characters in there, and that's true. We can also see some sprites. We can see the sprite frames in the first bank there. Right down at the bottom we can see that there's the minor sprite. You can see that the foot sprite comes down, and we can see what looks like some monster enemy frames. The pillar as well. Okay. We're warping through this now. The kernel load hasn't sped up. I've just enabled warp mode in the emulator just to really speed on through this load because it's going to take ages. So this is still loading and loading data from tape and storing data into memory. We can see that on the memory view of ICU. Being the standard kernel load, it is then going to do some verification steps, or at least it should do. It is, by the looks of it. So in this version of ICU, it doesn't seem to be displaying the reads that it's doing for verification. This is rather strange. The other alternative is that no, actually I don't think that there is an alternative. It's actually running the kernel load routine, and it should be doing a verify at this point, and it's not displaying the memory reads for the verify, but that's okay. It still seems to be loading. I mean, obviously it was loading. Just going to let this run now all the way to the end where that jump was. It jumped to 4000 in hex. So here we are, warping ahead, and watch the memory view in ICU. Let's see what happens. And there we go, there's a burst of green indicating it did all of the reads all at once. Okay. That's a bit weird, but fine. Anyway, there's the jump to 4000 hex. We can see that this is all of the loaded data. If we use the text screen graphics map window, basically we can start to see the loaded data. Moving through memory, we can start to see that there's some interesting data here and there. That seems to be a graphics screen, maybe, or maybe the colors for the bitmap mode, maybe. There doesn't seem to be much in the way of hidden messages, right? At least not using the lowercase rom character set. Apart from here, Manic Minor Software Projects Limited, converted by Chris and Chris. There are two Chris's. I'm sorry, Chris. There's a Chris and a Chris. One with the CH and one with the K. R. Anyway, so let's go through, and we don't seem to have much in the way of extra Sprite data, although that data higher up in memory, there we go. This looks kind of structured and quite interesting. So we can see the screen is actually a much smaller resolution than the Commodore 64 screen. We can see that there's about 4 characters left and right that aren't being used. So 8 characters horizontally not actually being used. The screen is centered horizontally, and vertically there seems to be some spare characters, at least, 4 or 5 character rows that aren't being used. Now I can't find a character set which matches this screen. This tells me that it might actually be a bitmap color screen rather than actual character screen, which is used for characters. It does also seem to match the layout of the bitmap title screen. We'll just double check this. And there we go, we've got a bitmap title screen, but it's all shifted across. So I'm kind of expecting this to be copied somewhere else into memory. At the moment the game code hasn't started. Oh look, we can see what looks like a whole bunch of compressed animation frames. I say compressed because they don't seem to be completely clean animation frames. They seem to be laid out a little bit like characters, so that the sprite data, the sprite viewer won't display them properly because they're laid out in memory in different ways. The characters are laid out in just 8 bytes per character, where each byte represents 8 high-resolution bits, and there are 8 rows for each character. The sprites, on the other hand, are 24 high-resolution pixels across and 21 pixels deep, and they are arranged horizontally, so there are 3 bytes of 8 pixels each, 3 times 8, 24. So 3 bytes of 8 pixels each horizontally on the sprite. So if we zoom through, we can see the bitmap in the right place in memory. Now, interestingly, the game is not in bitmap mode. The game is displaying a character screen from, probably, looks like it's lower down in memory because I saw the character sets animating. So one of the character sets was animating for the screen that's being displayed in the game. It's not that character set. That's the bitmap color screen, not the game characters. So let's go back, try and find the game character screen. Yes, you see that screen layout is animating as the bitmap screen animates. So yes, it's the color information for the bitmap that was displaying that and animating the piano keyboard basically. And we can see that the scrolling message is actually updated as bitmap data for the scrolling message rather than using a screen split. Very expensive way of scrolling a message, but okay, it works. Now the programmer does know about screen splits because in ICU I can sometimes see a screen split going on in the title screen, but okay. We can see here, very interestingly, that when it's displaying the game screens, even during the title screen, the track mode is displaying game screens, we can see it's using extended high-res text mode. Extended high-res text mode is not very often used in games, but it does allow an independent background and foreground colour to be used for high resolution characters. But the number of characters is vastly reduced, which is why we see small character set data. So we can see here that the debug view for the graphics map doesn't render the extended high-res text mode properly. It's actually reading characters that it shouldn't be reading from higher up in the character set that actually isn't being displayed by the Commodore 64. So instead of 256 characters in high-res extended high-res text mode, it's actually divided by 2 and divided by 2 again, so it's 64 independent characters, not 256. Because the upper bits of the character data are used to specify how the colours are displayed for the character cells. So the 4 background colour registers in the VIC, D021 to D0222324, are the 4 background colour register values which are chosen by the upper 2 bits of the character to display on the screen. Which is a really good way of having a high resolution graphics but with quite a lot of colour variation, which is a mode which allows quite compatible with the ZX Spectrum way of displaying high resolution graphics. The number of characters is limited, but for this type of game it doesn't seem to be causing too many issues. So we can see when the screens change, if we look at the sprites, we can see that the sprites are changing. So the sprites changed to show the enemy, and the enemy has 4 frames as walking left and right. We can see that when the screen comes on, actually the sprites flickered, indicating that they had been cleared and then decompressed from memory. So yeah, the character set screen at the moment shows what looks like the compressed data. So there seems to be little control bits or stuff like that actually in the sprites itself, which then get expanded into the real sprites. The main character actually only has 4 frames of animation facing right and 4 frames of animation facing left. There's the boot, which comes down and squashes you with the trouser leg, of course, and then there's the pillar. We can see that the main leg of the boot actually gets added to the screen as it's moving down for the game over effect. So what's interesting here is that the title screen is actually showing some black boxes in the far right hand middle part of the screen, but in the debug view it's actually showing some extra graphics which aren't displayed on a Commodore 64 screen. So I wonder what those are. They're probably just, it's probably just a badly converted bitmap screen, maybe. But yeah, there's an omega symbol and then a couple of keys which you can see in the graphics map. So yeah, let's go through the screens, and if you look at the sprites, we can see that the sprites are decompressing the animation frames for the enemies when the screens move, are progressed through in the attract mode sequence. Some enemies have left and right frames and these ones don't. That means that there were 2 independent enemies as opposed to having enemies with left and right facing frames. Interesting. So telephone, and then this weird spinning thing, and this ball thing, and this jumping up and down thing, or moving up and down. The eye, and then the pogo thing. Yep, there we go. So there are basically, up to 2 different types of enemies being displayed on the screen, either walking or pulsing or whatever it is that they do. There's the last screen. So the last screen. Okay, so the last screen, that's what it looks like. Okay. Oh, and there was a split there as well. If you noticed, there was a split in the background border color. Okay. Well, that explains that then. So the definitions for the animating main character, the number of lives that you've got left, they're just animating in the character cells. They're not sprites. Anyway, that's pretty much it for this game. It's a very small, simple little game, really. It's got a few little nice touches for graphical variation for its levels. And the use of extended high-res color mode is also, or text mode, is also rather interesting. So yes, if you like these kind of retro games videos where I have a little look about what goes on inside, then please do consider liking or subscribing to this channel and or adding a comment in the comment section below so I can see if you like what I do. Thank you very much for watching and have a great day wherever you are.